Good afternoon, everyone. Today, I'd like to talk about the Chainlink CCIP. Before I start it, I want to give you the big picture of what the CCIP means. It's a protocol that proposed by Chainlink, one of the most famous Oracle provider out there in the blockchain field. So CCIP actually stands for Cross-Chain Interoperability Protocol, which essentially is going to bridge two blockchains. We know right now it's the blockchain is too many of them, and they are not well interconnected to each other. But the vision is the blockchain is going to be like the internet, that net and net will be connected and form the internet. In the same way, we should be able to, in the future, at least that's the vision, that in the future we should be able to seamlessly use all the blockchain all together, like they are only one blockchain in the whole world. So this is what the CCIP is all about, bridging to a blockchain over here. So as you can see, there are two key components for this protocol. One is called OnRamp. The smart contract is on one chain one, and the other one is OffRamp. The smart contract on the other one. Right now, the new version, this is probably the new version now. The old version, you have multiple OnRamp on each chain and multiple OffRamp on each chain. Basically, for each lane, each source and destination, they have one. So now they consolidate so that on each chain there's only one OnRamp and there's only one OffRamp. So I draw it in this way, but you can imagine it's symmetric. So on the chain one side, you have one OnRamp and one OffRamp. And on chain two side, you have one OnRamp and one OffRamp. So for any traffic, go from chain one to chain two, you're going to start from OnRamp and then send the message over via event. And then through relayer, the relayer is going to send a message to OffRamp. So in this way, tokens will be able to transfer from chain one to chain two. Same for messages. So we're able to transfer both data and token from chain one to chain two via the relayer. Okay. So today I'm going to focus on the maybe the one of the protocol called RMNRemote. I might be able to mention a little bit about RMN home, which I didn't draw over here. Probably I should. So the RMNRemote is used for two purposes. One is to identify what other component are failure right now. Means you can mark something is not working. It's like a pause. It's like a pause functionality. You can pause any of the component using RMNRemote. But more importantly, is on the OffRamp side, you can call RMNRemote. There's a called a verify function to verify that the message we received on the OffRamp side they are really reliable and trustworthy. So basically, there's a bunch of signature in RMNRemote. It's going to sign the messages. Why don't we jump into the code of RMNRemote? Okay, so that's going to be RMNRemote over here. Okay, let me close the rest of them to make it more clean. So RMNRemote over here. So as I mentioned to you, basically there are two things important. One is you are able to mark if something is cursed or not cursed, which is in the managed in the let me show you, in the state variable called let me search for it. Why it's so hard to find it? It's called S cursed subjects. Okay, so this is the state variable that manage all the cursed component, and each component is identified by unique identifier of 32 bytes. So if you look at the struct of S cursor subjects, you actually see it's basically a set, so it's not a mapping. So it's just a set over here. So let's look at this one first because it's easy. Okay, so first of all, only the owner can curse and uncurse a subject. A subject is just an identifier, 32 bytes, 16 bytes, sorry. So just a 16 bytes so over here. So you are going to create a dynamic array in memory. In this case, only one subject. And then you call the internal function, which allows you to uncurse or uncurse. Let's look at a curse first. So you can curse one subject, calling a wrapper. This is a wrapper of the internal function. Actually, both of them are public. So this is external, this is a public, and it's only by owner. So so it's you go through all the subjects, and if it's not cursed yet, you are going to add it. And because this function, it doesn't matter if you add it twice. If you add it twice, it's going to say it's already cursed. So you cannot add a duplicate over here. So that allows us to add a cursor subject into the set, which is S underscore cursor subjects. All right. So if you're in that set, that means it's like, in the list. So that means this component is a problem. Otherwise, you can uncurse it. And in the same way, it's a similar, it's iteration, and you're going to remove it if it's not there. If it's not cursed in the first place, then it's going to revert. And then this is just simply get the list of all cursor subjects, return an array of bytes over here. And then we can check if it's cursed or not by calling is cursed. So this one, there's no argument. So that means there are only two cases. So this is two special identifier, a legacy curse subject, and the other is global curse subject. Okay. In either cases, anyway, it's going to call its curse. So this is more for global, I would say. If something, this is probably more serious. So if you don't give an argument, and if this returns true, that means you have a larger scope of trouble over here. Otherwise, you can be more specific over here, giving the identifier of the subject, which is the idea of the component. And then if the set contains it, or if it's global, then we are going to say it's cursed. So when there's a global curse over here, we always say it's cursed, but not for the legacy. The legacy curse subject is always here only. So so that means only the global curse subject have an inheritance that cover all the component, not for the legacy curse subject over here. Okay. So this function is more like a new one, I would say. Traditionally, it's more coarse-grained. You simply say it's a curse or it's not cursed. And now we are able to say, it's a curse for a particular subject. So that's very much for flagging the status of a component. The other one I would say is the project also maintain a list of signer using the idea of so-called configure. So what is a configure? Configure basically is a list of signers, okay? In addition with if, which is the threshold, how many bad signer we allow. So if you have if, that means we need to have F+1 signatures to sign off something. Okay, and so that's the smallest requirement to do that. Otherwise, we can try. Let's see. So this contract maintain two versions of configures. The two version configures are maintained in the variable of is configure right here. Okay, so it's configure. There's only one version. I'm sorry. But you can only manage one version, but this is more like the version number. So originally this is equal to 0, and every time you change this, this number is going to increase by 1. So that's very much of it. So for each version, I give one example over here. It's going to be look like this. Okay, so its configure will look like this. Basically, one is you have the RMN contract configure digest. So what is this digest? This digest corresponding to another file called RMN home. And here we have configuration 2 for the whole network. In particular, they have the dynamic configure and the version configure. Here you have the configure digest. Okay, you can have two versions of RMN home configuration, and then this configure digest represent a particular configuration. So it's like ID, primary key for the configuration. So that means we are linking the RMN home configure digest to here, so we know they have to work together. Otherwise, the signature will not pass. Okay, so let's look at this again. So you have a bunch of signer right here. You have the RMN compact digest, and then you have a bunch of signer. Each signer have an index. It's usually from 1 to 5. And then there's a threshold, in this case 2. So that means at least we have to have five signers. So in this way, you have, only need to have F+1. So if 3 of them sign off, then the verification is going to pass. All right, so let's dive into the code over here. So the constructor of the RMNRemote is going to be the local chain selector, which is where the chain is going to be deployed. So this chain, local chain selector in our diagram is going to be corresponding to chain 2. So chain 2, the index of chain 2 will be the chain 2 selector. Okay, it's where it's going to be deployed. So you're going to store it as I means immutable. So this is not going to change. It's I local chain selector. Okay. I think indeed it's going to be immutable. So yes, it's immutable. I local chain Merkle, and if you have S, means it's a state variable. So that's good convention. Okay. Yeah, that's a pretty good convention. So then the most important function I would say is the verify. What does the verify do? The verify is going to whenever one of the function in OffRamp is called commit. Whenever we commit the message root, which is Merkle root, into the blockchain 2, you have to call the verify function of RMNRemote to make sure that those roots are actually correct. Okay, ensure its integrity. They are signed by a group of signers. In this case, at least F+1 signers to sign off the signature. So let's look at how that can work. and the remote. So I'm going to look at now. So it's going to be a list of Merkle root over here. And then you have a list of signature. In this case, at least a +1. So if it's smaller than a +1, it's going to revert. So that's the threshold. That's the number of signature needed to sign off the Merkle roots. In addition, we are going to have OffRamp address over here. So that's corresponding to basically the caller, basically this guy. Okay, so the address of OffRamp is also included. So as a matter of fact, although this function is public, everybody can use this to verify it. But actually, the caller typically is going to be OffRamp address. OffRamp address is going to call this and check if the roots are valid before they committed to it. Okay, so they are going to calculate that address using the KitKat function. First of all, they are going to include the report over here. This is actually a prefix, I think, to stand for. It's a. Let me see. Yeah, it's actually just a prefix. Okay, this is Gene's KitKat function. All right, so and then it's going to be the report, which is the report is defined here. We have the destination chain ID. We have the destination chain selector. Okay, and then there's also RMNRemote contract address, OffRamp address, IMM home contract configured address. So all of these values need to be filled. So first of all, the destination is this destination because it's chain 2 in our example, right? And then the destination select is also this one, the local one, right? So because this RMNRemote is deployed in the destination chain right now. So this verification is used for the destination chain in this as far as this function is concerned. Okay, and then the RMNRemote contract address is this address. Okay, this particular address. So we are all talking about the target remote address over here. And the OffRamp address is also the one signed here. So everything is on the, in other words, all the argument we talk about is on the chain 2 part. All right. So just to make it clear. And then the RMM contract configured address in the same way, it's going to be on the chain 2 side as well for that particular configuration. So if somebody reconfigure the IMN home, then they need to make sure all the messages are already, already signed. So, and then the Merkle root is simply a list of the Merkle roots. So I believe that's just going to be a bunch of 32 bytes. Yeah, but we can take a look and see what the Merkle roots structure looks like. I believe it's just a bunch of, let me just search for it. Oh, okay. It's more interesting. It's more than I thought. It's actually also tells you the source chain selector. And then so the source chain selector is going to remember where the source is. So in this case, it's going to be Yeah, I really should look at more insight. So it's the Chain1's information regarding that particular message. So this is Chain1's information, the source chain selector, and then the on-ramp address also regarding the source chain. And then the main sequence number, max sequence number is regarding this root, because the root is the Merkle root of a tree, which is on the leaf side is all the messages. So this is the message sequence number. What is the minimum one? And what is the maximum one? Okay. And they are all sequential, supposedly. And then if finally is the Merkle root. So the capital Merkle root actually contains 5 fields. Okay, so that's good to know. But it doesn't have the chain ID, only have the chain selector. So I believe, and then if the source chain have a fork, I think that might be an issue. It's not going to say which source chain it's going to be. Let me look at this again. So okay, yes. Address, previous address, signed address over here. So let's proceed over here. Blockchain ID is this one. The local chain ID over here. And then there's going to be a loop over here in which we are going to check if we have enough number, if all the signatures are valid. So it's going to use the EC recover. This has to be a fixed value because you don't want to have signature manuality. So it's going to be over here. Yeah, it's a fixed value. I think it's a 27, and then you have R, you have S over here. So the sign address is going to be one of the signer's address, and so you're going to check if it's one of the signer, and basically this is a mapping to check if it's one of the signer, and you have to also make sure you save the previous address over here, and then you have to check that it's unique. So this line, if you have duplicate sign, then it's going to be bad. And in addition, there's also requirement that all these sign address have to be all these sign address have to be strictly increasing. If the previous address is greater or equal to sign address, or even they are equal, you're going to revert. So all these addresses will be sequentially increasing to make sure the verify is going to pass. The rest of them is just a configuration function. You can set a configure, and when you set, you have to make sure the IM home contract address is valid. It doesn't check against the IM home, so it's rely on the owner to be doing the checking offline, I believe. It's not going to call the IM home directory, and then and then here's the check that the signer has to be the index has to be in ascending order. If it's not smaller than, So they always have to be in increasing order. If it's not in increasing order, then it's going to revert. Okay. And otherwise, the number of center has to be at least 2 times A plus 1. And then this is also trying to clear the all the signature. So this is all the mapping done before. This is for the all the configuration for this mapping. So this mapping is cleaning up. And we have to clean each entry. Actually, for the mapping, it's difficult. You have to remember what to clear. You cannot simply clear a mapping without remembering which entry to clear. And then you have to set a new sign over here in the same way by doing this mapping. Okay, so this mapping is going to be stored. They have to check the mapping. They have to check the entry is there. So we are not going to override an existing entry. Otherwise, it's going to be signed. And then finally, we change the configuration and increase the version number by 1. And then and this one is get both the configuration as well as the version number. And keep in mind, we only keep one version, the last version. And then this is local chain selector. This is going to be the digest header, which is a digest of a fixed constant. So we already talked about this. So that's very much how RMN work. So in summary, we have to remember the Merkle roots over here. I think it's a new thing I learned today. The Merkle roots actually is not just 32 bytes. The verify over here, it's not just 32 bytes. It's actually good to know. It's actually this. You contain the source chain selector as well, but not the source chain ID. So that's something we can keep in mind. Thank you so much. Have a nice day.